Hi everyone, this is Manuel Portilla. Today, or in this recording, I'm going to be presenting you my thesis work, which is called a long-term generation and transmission expansion planning model, considering desalination flexibility and coordination, and it's a Chilean case study. This is a work that I already presented on the 20th of December of last year, on 2023, and this is just a recording because I couldn't manage to record that day. And in the first place, I want to give you a brief context and the agenda of what we are going to be studying today. First of all, I'm going to provide you with a brief introduction, then the methodology, the case study, the results, the conclusion, and the future work. And in these first slides or few slides, I just want to give you the context. And in fact, we are seeing that various electrical systems in the world have undergone a great transformation, mainly related to high participation of non-conventional renewable generation technologies. We are also seeing a need to find efficient ways to reduce emissions towards a zero emission scenario. And this gives and these two challenges makes that flexibility schemes or shows that flexibility schemes are becoming increasingly relevant and needed because of these two challenges. And in fact, new sectors can help on providing this flexibility, for example, demand response. And many industry sectors can provide this flexibility to the grid. We have the ones that have historically provided, such as the gas generators and some thermals generators. But now we have that demand response can do it, and as I mentioned, many industry sectors can, and it depends on their operational processes. And in fact, desalination is one of these sectors, and in fact, it is growing its capacity. Its capacity is increasing at a rate of about 7% per year since 2010 due to the growing need of fresh water. And in fact, and just going a little bit inside of the desalination process, reverse osmosis is the main desalination technology. It contributes the largest share of desalinated water production. The process, in just a sentence, it's a process where water molecules are forced to flow in an opposite direction to the natural osmosis phenomenon to obtain desalinated water. And reverse osmosis is a highly energy intensive process. And in fact, in this picture, I just want you to, which shows the scheme of a typical seawater reverse osmosis desalination process. I would just want you to focus on the part of the high pressure pump with the reverse osmosis system, because that's where the most energy is consumed. And in fact, in this study, we are going to be focusing also in this stage because we are, as we want to study the flexibility of a plant, we are considering in this case that we can change the operation point of the plant by shifting the frequency of operation of these high pressure pumps that increases the pressure of the water to make it flow through the reverse osmosis system, obtaining these two flows of brine and the fresh water. But yeah, I just want you to stay focused on the part where we have the high pressure pump with the reverse osmosis system, because that's where we are going to obtain the flexible operation of the plant. Also because of the water storage, but in terms of the plant, it's because the usage of a variable frequency drive on the high pressure pump. So just this is a lot of text, but I just want you to focus on some main ideas that we have found on the literature review. And in fact, we are seeing that in the last years, the research had taken a steer on flexible opportunities of desalination and its integration with renewable energy sources. We are seeing that they are tackling islanded desalination plants powered by decentralized renewable resources, for example. We're seeing the exploration of different operation strategies for desalination plants, how the grid operating changes when we have desalination, its integration with solar, photovoltaic solar or wind. So we are seeing an interest on this topic on the last years on the researches. So from here and from the context that I've given you, comes the motivation and the contribution of this study, where the idea is to provide an integrated generation and transmission expansion planning model that considers desalination participation in the power system, given the approximated physical constraints of and dynamics of the reverse osmosis plants, and exploring the flexibility opportunities that they could have in the first place, and also give some first slides for a desalination policy, for example, as desalination could mean an important not considered load for the power system. And now we are going to enter to the methodology, but it has 3 parts. Maybe it's going to be a lot of information, but the idea and the goal that we have here in this study is to be able to represent in the first place the desalination process in order to then consider it in the power system planning model. So we want to represent the reverse osmosis process, represent the energy consumption of the process, and that component consider it on the power system planning model to be co-optimized with the generation and transmission infrastructure, and also the reverse osmosis or the desalinated water system infrastructure. So here we have an overview of the optimization model, where we are in the shoes of a centralized planning figure that optimizes both the power system and the desalinated water system. And they both have their own cost components and their own constraints, but they are linked in this red component, which is for the desalinated water system, the energy consumption of the plant, which is included in the power balance between load and generation in the power system. So we have a mixed integral linear programming model, and it's based on Switch, which is a platform for planning high renewable power systems. And as I mentioned, we have this desalinated water system, but in fact, as we want to consider it and we want to build a module of the desalinated water system to include it in Switch, representing to be represented in the optimization model, we have to give a previous step, because reverse osmosis plants are usually modeled and simulated with the solution diffusion model, which describes the performance of the reverse osmosis process and how the flows and concentrations of the solids change accurately. But the thing is that the equations of the model are highly non-linear, which makes its implementation in this proposed expansion planning model very difficult. So in order to consider the operation of the plant on the mill planning model, we have to give or to take a previous step to obtain a linear relationship between the permit flow produced and the energy consumption associated to it. So really summarize, this is the algorithm that we modeled to obtain this linear relationship between the model. And the approach that we take consists of searching for the range of feasible operation frequencies for a defined plant by testing an input frequency on an optimization model containing the equations of the approximated solution diffusion model. So in Spanish, we have operating range of the plant, and by shifting the frequency or the input frequency that the high pressure pump has given by the variable frequency drive, we can move through this operating point, and this is going to have an associated or the parameters constrained by the solution diffusion equations are going to change throughout this frequency range. So at the end of the day, what we want to obtain is, by trying all of these frequencies, we want to map the operation point, and we want to map at the end of the day the relationship between the permeate flow that we are going to obtain from the plant, which is the fresh water, and the energy consumption associated to this. So at the end of the day, the algorithm is defined to obtain the feasible frequency range of operation of each of the defined reverse osmosis plant available to be installed. So we are seeing that, and the results of this part are shown here. We have many parameters that affect the solution diffusion model and affect the production of fresh water. And one of them is temperature. And as we are seeing a Chilean case study, we see that throughout from north to south, the water temperature changes, and also throughout the year, it's going to change. So we are going to see, and we have, and the image shows that we have some seasonality on the process. And in fact, we see that for the month in winter, we have a much more narrower range, and for summer or more warmer months, we have a wider range of operation. So here we have in the x-axis the permeate flow produced by the plant in cubic meters per hour, and we have the total energy consumed by the plant associated to it in kilowatt hours. So having this representation and this linear relationship that at the end of the day is a slope and an intercept of for each representative day, we have the desalinated water system model, which consists of the operation of the desalination plants based on a forecasted water demand provided as an input in each water zone, where the desalinated water demand must be supplied in the most efficient way. And the desalination model is divided into equations for the plants and water tank, for investment and for operation. And some of the main parameters of the model are the location of the plant, the electrical node where they are going to be connected, the water demand of the zones, and the flexible operation parameters, and which we obtained on this previous step, and also the fixed and variable costs associated to the investment and the operation of these plants. And now, digging a little bit deeper on the model, we have first of all the components associated to the power system, but I'm not going to stop. But the model minimizes the net present value of all investment and operation costs of the power system and also the desalination system. Then we have the constraints, where for the power system are the investment constraints for generation and transmission. We have the power balance constraint, the generation and dispatch transmission constraints. We have the hydro system constraints, also the energy storage constraints, and also the concentrated solar power constraints, which are based on the work of MENA on 2019. And then we have the part for desalination, where we include in the objective function the investment and operation cost of desalination. We see that the added components are fixed investment cost of a plant. We have fixed investment cost of water storage. We have the fixed operation and maintenance cost, and also the variable operation and maintenance cost. Then in terms of constraint, we have a group of constraints added to the model, which first of all, for the plant, we have the total units built of the plant on each of the periods, which is the accumulated capacity or desalination capacity of each plant. We have the minimum and maximum amount of desalinated water that a plant can produce. We have the water balance of the plant, because we are saying, and in this study we say that the plant can either send water directly to the demand, or it can send it or store it in the water tank. Then we have the energy consumption constraint, which at the end of the day is added to the energy balance equation of the power system planning model, which links both of these systems. And here is where the linear approximation that we made comes to play. Then we have the water tank constraints. Here we have that the main water tank equations are that again the tank total capacity built, which is the accumulated storage capacity on each period. We have the water conservation between hours, and we have also tank storage and supply limits, which consist on maximums and minimums and the border conditions of the storage. And finally, we have the water demand supply balance, which is the balance between the demand and the supply of water. And here the demand is said to be supplied by either the water that we have stored on the water tank or the water given by the reverse osmosis plant directly, or both of them. It can be a combination also. And now entering to the case study. For the power system, we are seeing the Chilean power grid, which is modeled as 26 nodes, and it's an approximation of the national electrical system. We are in the scope of the project is from 2025 to 2040, considering 12 representative days on each investment year to capture the planning and approximated operation dynamics for the different scenarios proposed. And the basis scenario is set to describe a tentative pathway course to carbon neutrality by 2050 of the Chilean power system based on the data developed in the long-term electrical planning process done by the ministry. Then for the desalinated water zones, we have that they define the places where desalinated water is going to be used as a resource, and the definition of them is based on the concept of a hydrographic basin, which also is based on high water shortage levels obtained from a few studies where they mapped the more stressed basins in Chile, and from these reports, we clustered them in 13 critical zones, which are shown in figure 8 in red, and in the table with the associated code, the associated electrical node, from where they are going to consume energy, and the basins which are in this cluster. Then we have the desalination demand, and here the forecasted desalinated water demand depends on various factors, such as increasing water stress levels, the evolution of the different water demand sectors, also water use policies and efficiencies regarding water usage. And in fact, it's based on we based in Caldera and Breyer, and also the DGA water demand projections for 2030 and 2040. We defined 3 scenarios of desalinated water demand based on the first study and the methodology that they used. And they are the base scenario and irrigation efficiency push scenario, and also a scenario with the highest possible irrigation efficiency, which only changes the amount of desalinated water demand that we are going to require in each of the periods that we are looking on this study. And with all of this information and all of these parameters that I mentioned in a summarized way, we have the proposed scenarios, and here they are constructed by joining each of the different desalinated water demand levels, which I described in the previous slide, with the different operation configurations of the plants. So we have 3 main scenarios, which is the base scenario with no desalination, and then 2 desalination scenarios. And the first one is the base irrigation scenario, which consumes the most desalinated water, and then the highest possible irrigation efficiency scenarios with the lowest energy and lowest water demand, or desalinated water demand. And inside of these 2 desalination scenarios, we have three sub-scenarios where in the first one we consider only inflexible plants without water storage with constant electricity costs. Then we have flexible plants with storage and also inflexible plants with constant electricity cost. And finally, we have the same flexible plants with storage and inflexible plants, but now with variable electricity costs. To also capture and analyze what happens when the electricity prices that the desalination plants pay affects the operation of them. And for the results, we first of all see that for installed capacity and generation technology share, we see that more energy generation capacity is installed for scenarios with flexible plants. But we see that the combination of solar and battery storage is more sensible to the amount of water needed and the tariff, showing that there are some synergies and compatibility with desalination. And this is also because the desalination plants are said to be and forecasted to be more needed in the north and the center, where also solar is the we have a lot of resource there. Then in terms of the systemic cost comparisons and the benefits of optimization, we see that optimizing both systems increases considerably the total cost, but flexible scenarios achieve in some cases more efficient results. We see that optimization of both systems allows to reach more efficient outcomes in all the scenarios. And in the base irrigation efficiency scenario with flexible plants, in fact, a 16% reduction of the power system cost was achieved when optimizing both power and desalinated water systems. Now, in terms of emissions and the evolution of emissions, we see that the overall emissions increases when with the use of desalination, mainly because gas generation on periods when solar energy is not as available as it could be. And this showed that the efforts to decarbonize the energy sectors, the energy sector in 2050 is going to be harder when considering new demands and the increasing on the demand, challenging more the transition to a net zero scenario or goal. Then in terms of plant and tank investment, we see that when more water is needed, of course, more desalination plants are built, but as flexible operation is allowed, there is a reduction in the number of plants required. We also have that the optimal mix of plants built is affected by the structure of the electricity cost and also by the type of energy generation projects in the associated electrical node. And finally, for scenarios with expected variable electricity cost for the plant, the system's optimal transition is to invest in water storage in order to shift the production for hours where the costs are cheaper and when the power grid is less stressed. And in terms of the usage of this water storage, we see that it allows for efficient water utilization and management, reducing the need for instantaneous production, particularly when we have the variable frequency drive. We have also that when we compare the water produced when we have a variable frequency drive and the water produced when we don't, we see that that including this BFD leads to a reduction in the water produced, meaning an optimized and more controlled water supply strategy. And now, in terms of the energy consumption of the desalination process in general, along the whole power system, we see that the electricity cost affects the desalination load curve, which increases the shifts of energy consumption in particular hours of the day. And in fact, when flexibility is available in desalination operation, we see that plants are used during solar availability, shifting the production. And finally, in terms of water cost, we see that costs are similar, but for cases with higher water demand expected, the values are smaller than when less water is needed. So we could see a bit of scale economies And we have also that scenarios that include variable frequency drive generally tend to have lower levelized cost of water compared to constant scenarios. And to close the presentation and the recording, for the conclusion and the future work, first of all, we see that desalination is going to be a relevant electrical load in the coming years as the impacts of climate change are traduced in higher water scarcity. Um, and but we see with the results that the generation capacity under desalination participation scenarios increases considerably, reaching almost 32% more installed capacity in 2040. And we see, and related to these first 2 points, that the combination of generation technologies joined with desalination plants' energy consumption creates valuable synergies for the power system when considering and assuming that desalination is going to enter uh, as a new load in the system. And we see that investment in desalination plants and water storage tanks is influenced by the water demand, obviously, and the electricity costs used used to operate the plant. And finally, we have that the different defined scenarios have shown different outcomes on the strategies of operation and investment of the desalinated water and the power system, but including flexible plants in the available investment portfolio, reverse osmosis plants led to more efficient systems in terms of total cost. It's a small reduction, but it's uh, it reduced the costs, the total cost. And in terms of political or policy impacts of the results, we see that optimizations of both systems allows more efficient outcomes in all scenarios, showing that starting to elaborate a centralized and coordinated regulatory framework is extremely relevant to achieving an efficient development of this technology. We also see that one of the main challenges for the near future will be setting the regulatory framework to give the right economic signals to incentivize and orient the operation of desalinated water infrastructure to a flexible scheme. And it's also interesting to analyze from the regulatory scope the scheme to coordinate the operation of the plants, to open, for example, opportunities for new entities, such as an independent water system operator, for example, um, or participation in current or new demand response mechanisms. And finally, even when mainly all generation capacity installed is renewable, carbon emissions increase for years 2030 and 2040, making efforts to decarbonize the energy sector to 2050 even harder. And just for future work, the dynamic of the operation, and particularly desalination constraints such as minimum on and off time in greater detail were not studied in this work. So understanding and modeling water supply for scarce areas in detail, considering water transport through pipes, becomes relevant to understand the impact in a local framework. Also, from again a more local point of view, desalinated water demand is going to be needed in more than one sector, so multipurpose plants are going to be a more efficient solution. So exploring and considering different water demand profiles on these types of studies would provide interesting insights to understand and to see the real value in a local perspective for different nodes and different load the water demand profiles in each of these zones. And it's also necessary to design participation and coordination schemes for desalination plants through correct economic signals. So studies on possible participation in the market or ancillary service of these plants are also seen as research opportunities. These are the references. And yeah, this has been my work, and thank you for seeing the recording, and just to make sure again that this is a recording and it's not the thesis defense um of of the day. So thank you very much.